Hello again, students. I wanted to wrap up our discussion of these proofs on complex conjugates. As you can see, I've got the answers kind of laid out for you here in this document. On exercise 300, this is simply a proof that whenever you take the sum of a complex number and its conjugate, you're going to be left with just the real number portion when you take 1/2 of it, because obviously the sum is going to be 2 times a, so 1/2 of z plus z bar is going to equal a. And exercise 301 does a similar thing, except now it's with differences. When you take a complex number, just shorthand here, they're representing it with z instead of writing out the a plus b bi right here, okay? But a plus bi minus a plus bi, or z minus z bar, is going to give you, well, that'll give you 2bi, and instead of taking 1/2 of that, we're going to take 1 over 2i, and that's going to leave us with just the imaginary portion of z, which is represented by the b, the coefficient that you multiply I by. And 302 is something I alluded to yesterday. That is, when you take the product of a complex number and its conjugate, you're going to be left with a squared plus b squared, which of course is going to be an element of the non-negative reals. Okay, so we're going to move on. Exercise 303 is just a conjugate mapping here. What they're saying, we're doing a conjugate mapping over the complex numbers, and we can prove that it's isomorphic to itself. And of course, whenever you have an isomorph to the exact same operational system, what you have is an automorph, as I defined last Friday. So anyway, this is the proof of that, just that once again, showing that the mapping is going to be 1-to-1 and onto, and that it's going to be homomorphic from the field of complex numbers to the field of complex numbers. And of course, when the operational system is the same, it's not just an isomorph, it's an automorph. Okay, moving on to rationalization of complex numbers, as shown right here, with this 2 minus 3i over 3 plus 4i. We'll want to rationalize the denominator by multiplying by the conjugate. We did a similar thing with square roots earlier in the year, you may recall. So yeah, yet again, 3 plus 4i is 3 minus 4i, but of course I have to multiply by that same value on the top and the bottom. And we use FOIL method, of course, to multiply this out. 2 times 3 is 6. And you get minus 8i, minus 9i, and plus 12i squared, which simplifies to minus 12. So 6 minus 12 is that negative 6, as you see right here. And then minus 17i. Meantime, the bottom, the most important thing is that property number 10, as I described up the page there a little bit. It's going to give us a real number denominator. And yeah, we'll just have 25. So I can, and of course, I can write it like this. If you're writing it on a test, that's fine. Also know that this is a way to represent that. Indeed, this is the preferred way in complex form, because now you've got it in that form of a plus bi. Cool. So some practice exercises here for you, starting with 304, as you can see. As you can see with this 2 plus 3i quantity squared, be careful with this. I mean, I filled in the answer for you here, but I wanted to be clear that this is found by taking 2 plus 3i times 2 plus 3i, and you do the FOIL method. 2 times 2, of course, is 4. 2 times the 3i, 3i times the 2, and 3i times 3i, of course, is plus 9i squared. So, obviously, these things are going to simplify a bit. Whoops. Well, that 9i squared, of course, that's going to become minus 9. You understand, I hope? Yeah, in the meantime, I mean, obviously the 4 is not changing. And, of course, I guess I can combine 6i and 6i. But here's my point. We add the 4 and the negative 9 part. And what am I left with? Yes, I've got the negative 5. And then I've got the plus 12i. See? There's the plus 12i and the negative